Now, part of what we're going to look at today is mathematical induction. This is a type of proof. Introduction. So, in this section, we'll study a form of mathematical proof called mathematical induction. And using this here is kind of a way to start. If we look at these sums here, well, S of 1, so we're adding all of the odd numbers together. Well, for 1, it's 1 squared. For S of 2, well, the first two odd numbers, 1 plus 3, is the same as 2 squared. For the first three, 1 plus 3 plus 5 is the same as 3 squared, going on and on. And what it works out, and it appears that S of n is equal to 1 plus 2 plus 3, going all the way out to plus 2n minus 1. Because 2n minus 1 would give us the next odd number, however many it is in the sequence, is going to be equal to n squared. Although this particular formula is valid, it is important first to see that a recognition of a pattern and then simplifying and jumping to conclusions that the pattern must be true for all values of n is not a logically valid method of proof. Just because we've seen it for the first so many doesn't mean it's going to work for all of them, because there might be one out there eventually that it doesn't work for. So what we do is we use this mathematical induction to show that it is true. And the way that this is worked, so the conjecture is true for these here. So let's actually delve into this, because I think, let me make sure. Because I think that's the one we actually end up using for it. Yep, okay. A lot of talk, okay. Well, I just want to actually look at this, because it's going to make more sense us actually looking at it, that it will be kind of talking all the way through it. Might work for some, but let's actually look at this here. Now, the way that mathematical induction works, it works in two parts. Part one, we show it true for the first term. So the very first term, we show that it is true. So for this here, well, that would be saying S of 1, well, that's equal to 1, which is supposed to be the same as 1 squared, and well, 1 squared is. So it is true for 1, yes? Now the next part is we show that it is true for n plus 1. Because if I can show it for n plus 1, for any value of n, it's just the next one after n, yes? So that means anyone after n will always be true. Because if I can show it for this here, then it's always true. Now to do that, we're going to assume n is true and show that n plus 1 is true. So we assume n is true, and then we show that n plus 1 is true. Well, so far we've already showed that this does work for the first term. So we have at least a basis to start with. Okay, now what we are going to assume is that S of n, which is equal to 1 plus 3 plus 5 plus 2n minus 1 is true. So we're assuming this statement is true. Now, let S of n plus 1. So we have this here. We want to show that this is true, that all of this here, which is equal to n squared, what we want to show is that S of n plus 1 is equal to n plus 1 squared. Because if I can show that S of n plus 1 is equal to n plus 1 squared, it means that anyone after the nth number will be true. And since n is the last one, well, anything past the last one is always going to be true. Because once we can show that the nth plus 1, the one after the next one, is true, doesn't matter which one in the sequence we do, it's always going to be true, continuing on and on forever. So, well, S of n plus 1, well, that's going to be the same as 1 plus 3 plus 5 plus 2n minus 1 plus 2n plus 1 minus 1, because we're going 1 after the nth term. Because it's going through here, so we have n, well, the next one after n, we're adding 1 to it. We're going to the next term in the sequence. Questions on this here so far? So really, this is all the original term, and if we want one more, we add n plus 1. Because n, the next one after n, is n plus 1. Questions on this here? Does that kind of make sense? Yeah, we're adding 1 to n. Now, we already assumed that this is true and it's equal to n squared, yes? So we already know that this whole thing here is n squared because of our original statement for s of n, 1 plus 3 plus 5 all the way up to 2n minus 1 is n squared. Now the book will go and say that this is all s of n plus 2 times n plus 1 minus 1. But s of n we know is n squared. Because that's what we said, yes? Now here, we'll simplify a little bit. We can distribute the 2. 2 times n is now what is our goal? N squared, n plus 1 squared, yes? So that's what we want to show. Is this factorable? So, is equal to n plus 1 squared. So therefore, it's true by our mathematical induction. Because we're able to show that the first case is true, and assuming that the nth case is true, we'll show that the one after it is also true. So it means that this does work for any numbers in the sequence. And this is what we did. We showed that that is true. So, by combining the results of parts 1 and 2, you can conclude by mathematical induction that the formula is valid for all integers n greater than or equal to 1. And that's all we have to do for this here, to show that this is true. It occasionally happens that a statement involving a natural number is not true for the first k minus 1 positive integers, but true for all values of n greater than or equal to k. So we could have a point where it does work or doesn't work after a certain mark. So that's why we have to do this here. In these instances, you can use a slight variation of the mathematical or the principle of mathematical induction, which you verify pk rather than p1. This variation is called the extended principle of mathematical induction. Really, since we can't start out at the first term, we have to start out at the kth term. It's just adjusting the numbers so that our first term works. First term, quote unquote, works. It's kind of moving the numbers over. When proving a statement, the only statement that you need to verify is P of 1 with actual numbers. The rest of it we're using are in cases. I'm going to steal your yearbook since it's already open. Because what I'm going to grab is another example that we can use. Mhm. So what we wanted to show is this here and prove it by mathematical induction. We want to show that this statement is true, that S of n, that the sum of any n numbers, the sum of their squares, is equal to, well, this formula here, n times n plus 1 times 2n plus 1 over 6. Because if we can show this here, then it does work, and it actually does. We start off always with S of 1, which is 1, which would be 1 times 1 plus 1 times 2 times 1 plus 1. Well, that's this first one's not going to affect anything. 1 plus 1 is 2 times 1 is 2. So it works for 1. Now S of n would be 1 squared plus 2 squared plus 3 squared all the way up to plus n squared, which is the same thing as what we all over 6. Now what we want to show is that S of n plus 1 is equal to, it's still all going to be over 6. We're going to have n plus 1 times, we'll have n plus 1 plus 1, n plus 2, times what would be 2n plus 3, because 2 times n would give us 2n. 2 times 1 is 2, plus 1 is 3. So S of n plus 1 would be 1 squared plus 2 squared plus 3 squared plus n squared plus n plus 1 squared. So we have all this here. Now, because of our original assumption, we know all of this here is n times n plus 1 times 2n plus 1 over 6. Yeah, this is what we have, the one in green. But we add to it n plus 1 squared. Well, to get these on the same division, to be able to actually add the fractions, I've got to multiply this by 6 over, which really just gives us 6 times n plus 1 squared. Here I have n times n plus 1 times 2n plus 1 plus 6 times n plus 1 squared. See what's the best way to do this. Yeah. I don't know how the book is gonna do it because the book might have an actual easier way to look at this. I'm gonna factor n plus 1 out of both terms. And it's gonna make it a little bit simpler because if I factor it out of here, I've got n times 2n plus 1. And over here I have 6 times n plus 1. So that makes it a little bit easier to work with. A little bit. Now what we can do is we can simplify this down because we'll need to combine like terms and move things around and then factor it back out. So we can multiply 3 by n, which would give us 2n squared plus n plus 6n plus 1 over 6. n. That's what I was just wondering myself, because I multiplied wrong. Because it should be 6 because of the 6 times n plus 1. No, thank you. That makes more sense. Now we can combine like terms, which will give us 2n squared plus 6 over 6. Now we do need to factor this thing. Well, since the 6 is positive, we're going to have plus and plus. Now, I'm going to put 2n and n. I'm doing it this way because, again, because what we wanted to show, we had n plus 1, n plus 2, and then 2n plus 3, because we had n, 2n. So I'm kind of keeping it in that same pattern. Now, the factors of 6 are 1 and 6, or 2 and 'Because 2n times 2 would give us 3 times, so n times 3 would be 3n, plus 2 times 2n would give us, yep, but wait a minute. What did we want to show? That n plus 1 is equal to n plus 1 times n plus 2 times 2n plus 3 over. So we're able to show that it is true. So this does work for the sum of any number of squares will be this here. And this is a way to show that formulas and theorems do work when we take them out exponentially, or not exponentially, but take them out to the nth extreme. Take them all the way out. And that's what we do with those there. Does that kind of make sense how mathematical induction can work? For the most part? Yeah, we're just proving that it works. Now, mathematical induction is not always a surefire way to solve it. It doesn't work every single time, because it's hard to see what the pattern is or how it fits, and you have to have the constraints and everything that works together. So it is a method for proving. It is not the surefire method. Although choosing a formula on the basis of a few observations does not guarantee that the validity of the formula pattern recognition is important, or validity of the formula. Pattern recognition is important. Once you have a pattern or formula that you think works, try using mathematical induction to prove it's true. Because we can calculate several terms in the sequence, it is often a good idea to write the terms in both simplified and factored form, try to recognize a pattern, and then kind of testing our hypothesis and conclusion. So we can find a formula for the sum to prove that this here is true. So we can set it up as S of k is equal to 1 over, all the way out to k over k plus 1. To prove the validity of this hypothesis, use mathematical induction to do this and kind of showing it through. And we could go through and do that, but I'm not going to worry about that, because I'm not going to actually make you guys do this here. I wanted to show you what it is and kind of so you can see it. Now, the sum of the power of integers, these are kind of cool. The sum of the powers of integers to the first. So 1 plus 2, just adding all the way up to the n is equal to n times n plus 1 over 2. And it works out every single time. So let's just do one that's easy to do. Let's say 10. So it would be 10 times 11 over 2, yes? 10 divided by 2 is? Times 11 is? So in the calculator, do 1 plus 2 plus 3 plus 4 plus 5 all the way up to 10. You want to do it once? It is 55, and it works for any of them. Then we have our squares, which we used and proved a minute ago, cubes, fourths, fifths, and any of these here. And it's a simple way to go through it and find it. So if we want to find the sum of each one of these here, so for our cubes, n squared times n plus 1 squared divided by 4. So n squared, 7 squared times 7 plus 1 squared divided by 4. Formula, yep. Well, 7 squared is 7 plus 1 is 8. Squared is 64. And luckily, 64 divided by 4 is 16. And then we just need to do 16 times 49. Or 49 times 64 divided by 4. Either one will work. Yep, I took those off. So it's 784. And that's it. Now, could we have plugged, especially since these aren't too big, could we have plugged this into the calculator? Yes. On the graphing calculator, I is not the imaginary I. It is x. Because it's saying I equals 1 to 7. So what it's doing is every time it's replacing I with 1 to start with, then 2, then 3, then 4, then 5, going up the sequence. Yeah. Yeah. If I were to type it in the calculator, I'd type it in like this here. And we can do the same thing with the other one here. Now, the way that we would do this by hand, I don't know what I'm trying to write. We would do x is equal to 1 to 4, but because they're subtracted, what we can actually rewrite this as is 6x minus the sum of x equals 1 to 4 of 4x squared. And we actually use the properties of these sums to say 6 times the sum of x equals 1 to 4 of x minus 4 times the sum of x equals 1 to 4 of x squared. Because they are constants. They're a constant number. They're not being affected by this term at all. If it was 6 to the x, we can't do it because of that number getting plugged in is going to go for 6. Because 6x, well, the first term would be 6 times plus 6 times plus 6 times. There's going to be a constant term of 6 that we can factor out and multiply in later. But then we'd figure this out here, which aren't too bad, because we'd have 1, 3, 7, 11, 4 plus 3 is 7, 8, 9, 3 is 7, 8, 9, 10 actually, is 1, 3, 6, 10. Because our squares would be 1, 4, 9, 16. Which we should anyways. Because n times n plus 1 divided by 2. 4 times 5 divided by 2 would be 2 times 5, which is 10. The n squared one, I don't, n times n plus 1, 2n plus 1. So n times n plus 1 times 2n plus 1. 4 times 5 is 20, times 9 is I knew I was a little off. 30. So this should give us and that's it. That's kind of what we would do with this here. Now, I don't have the page number. Yep. $649. 646.
You were close, but let's go.
47. 45 through 50. So pages 45 through 50, or problems 45 through 50 on page 646.